Have you ever wondered how large language models, or LLMs, are trained to understand and generate text that's almost human-like? These models, underpinned by deep learning architectures, have been making waves in the field of natural language processing, or NLP. They've been impressing us with their ability to generate text, translate languages, summarize lengthy documents, and even answer questions. The likes of GPT, the generative pre-trained transformer, have become household names in the world of tech. But how do these models become so proficient? It all starts with data collection. A rich, diverse dataset is sourced from an array of text documents, such as books, articles, websites, and social media posts. The quality and variety of this dataset are instrumental in determining the performance and generalization abilities of the LLM. Once the data is collected, it goes through a process of cleaning, tokenization, and normalization. Cleaning is all about removing noise from the data. This includes HTML tags, special characters, and other irrelevant information that can skew the training process. Then comes tokenization, a process that breaks down the text into smaller units, typically words or subwords. Lastly, normalization, such as lowercasing, is performed to ensure consistency in the representation of the text data. Now let's talk about the architecture of the LLM. It defines the structure of the model and dictates how it processes input data to generate output. Transformer architectures, with their encoder-decoder structure and self-attention mechanisms, have become the go-to choice for LLMs. They excel at capturing long-range dependencies in sequential data, like text. The encoder is often used for tasks like text generation, while the decoder is used for tasks like machine translation. The self-attention mechanism allows the model to weigh the importance of different words in a sequence when making predictions, capturing contextual information effectively. The training process of LLMs typically involves pre-training on a large corpus of text data, followed by fine-tuning on specific tasks if necessary. During pre-training, the model learns to predict the next word in a sequence given the previous context. This is done through techniques like masked language modeling, where certain tokens in the input sequence are masked, and the model is trained to predict their original values based on the surrounding context. Training LLMs is no small feat. It requires a blend of sophisticated techniques and strategies to tackle challenges such as computational complexity, overfitting, and optimization difficulties. Gradient descent-based optimization algorithms like stochastic gradient descent or ADAM are commonly used to update the model parameters during training. Hyperparameters like batch size, learning rate, and optimization schedules need to be carefully tuned to achieve optimal performance. And to prevent overfitting, regularization techniques like dropout and weight decay are employed. So to recap, training LLMs is a multi-step process. It starts with collecting a diverse and high-quality dataset. The text data is then pre-processed through cleaning, tokenization, and normalization. The model is built on a transformer architecture and trained through pre-training and fine-tuning processes. Throughout this, a range of techniques and strategies are employed to overcome challenges and ensure optimal performance. And that, in a nutshell, is how large language models are trained.